Thank you. We're now changing over to the next topic of our class today, which is CMOS technology. Before I start this, I'll ask you a few questions about the nMOS technology. In nMOS technology, one important thing I mentioned in the last class, and that was adjustment of threshold voltage. Question is, how is it done? Any one of you? How the threshold voltage of an nMOS is adjusted? It was discussed in an earlier class. By using a step called channel implantation. Channel implantation. I told you that before the polysilicon gate is deposited, we carry out a low voltage, low energy, low dose implantation, usually of boron ions, into the channel region, which adjusts the value of the threshold voltage. Why it is so important? Because nMOS has got a tendency to remain, to be used, to automatically to be formed as a depletion mode MOSFET initially. For the reason, I think I have indicated in the class. When you grow the oxide on silicon for gate oxidation by a dry thermal process, that means by treating in dry oxygen, in the interface between oxide and silicon, in the oxide side, a positive charge is developed automatically. And that positive charge is normally referred to as fixed oxide charge. It is located in the oxide, but close to the interface. And this fixed positive charge, which is static, which is not mobile, which is a permanent charge, not a temporary charge, arising from the unsaturated bonds in the non-stoichiometric layer in the interface. This positive charge attracts electrons from the substrate. Substrate is p-type, in nMOS substrate is p-type, attracts electrons from the substrate and repels holes. Therefore, a depletion layer will be created at this surface, and not only the depletion layer will be created at the surface, there may be sufficient number of electrons at the surface to cause inversion of the channel. That means the source drain will be shorted, even without the application of a gate bias. Even if I do not apply any gate bias, the source drain may be shorted, that means device may remain in on condition naturally. And that is what is known as a depletion mode MOSFET. And that is a tendency for any MOSFET fabrication initially, after the fabrication, if you don't do other treatments, then it will come out as, there is a possibility that it will come out as a depletion mode MOSFET. But I have seen that using only depletion mode MOSFET, we can't realize good logic, because our today's logics are all positive logics. Everything works with positive supply. And therefore, it is not preferable to have any other kind. And one supply positive, the other supply negative, these are all inconvenient things today. So your transistor, one cannot avoid enhancement mode transistors. Now, how to do that, I discussed earlier, the last day, in the last class, that if you carry on some very low dose, low energy implantation of the channel region, usually, normally employing boron ions, then we can adjust the threshold voltage to a value which turns the device off in the normal condition. That means we can create a transistor of any threshold voltage. If necessary, I can make a depletion mode transistor of a given threshold voltage, or if necessary, I can create a enhancement mode MOSFET with a given threshold voltage. And these requirements are very important requirements in today's advanced MOS technology. And we shall see that in CMOS technology, this is more important than in nMOS. What is CMOS? CMOS technology combines on the same channel, same substrate, both nMOSes and PMOSes. By forming an inverter with opposite channel MOSFETs, one can show that the power dissipation can be minimized to an amazingly low value, very low value. CMOS inverters are the lowest power consuming inverters of all logic families, whatever available. Please remember this. And there we have to have both successful PMOS and nMOS technology implemented on the same substrate simultaneously. That is why CMOS technology is the most complicated technology compared to PMOS or nMOS. But today the technology has been matured to such an extent that all technologies, all MOS technology we mean today, CMOS technology, and neither nMOS technology or PMOS technology. Please remember. But what is the problem of CMOS technology? You see that for nMOS, the substrate should be P substrate, P-type silicon, into which you create N-type sources and drains. On the other hand, for PMOS, the substrate should be N-type, and you have to create P plus diffusions or P plus tubs for sources and drains, and these two are contradictory. So how can you do both simultaneously on the same substrate? And that was a challenge earlier, but gradually that challenge was that technological hurdle was solved, and now CMOS technology comes with usually called an N-well CMOS process, N-well CMOS process, or twin tub. Many terminologies have come. So we shall discuss now a CMOS which has got N-type wells. Let us see what it is. So this one is the layout of a typical N-well CMOS. Anyway, as I told you that this is the layout of a cross-section of a typical N-well CMOS, you see that here that modern technology, people use a P-type epi layer on a P plus substrate. That is a starting substrate. That's the modern CMOS technology. But earlier, they were using a P-type substrate only. But nowadays, instead of using a P-type substrate, they are using a P plus thick substrate. Wafer is P plus, heavily doped, heavily boron doped silicon substrate on which there is a thin P-type layer, which is not that heavily doped. The typical concentration of the epi layer may be 10 to the 15% immediate cube, whereas here it is in excess of 10 to the 19% immediate cube. Please remember, the substrate is very heavily doped, whereas the epi layer is thin. Thickness varies from 1 micron to 3 micron in today's technology. Thickness of this epi layer varies from 1 micron to 3 micron. And its concentration of this P-type epi layer is around 10 to the 15% immediate cube. Okay? Then, as I told you earlier, that we use oxide isolation. to isolate the different devices. These are very thick oxides surrounding the different diffuse regions or implanted regions. You remember the purpose of oxide isolation is to reduce or almost eliminate the sidewall capacitances, so that it can be used to very high speed, high frequency operation. Okay? Then in the left hand side, as indicated, there is an extra diffusion called N-well formation. This is an N-well formation, whereas N-well is not present in the right side. So in the left of this line, we have the PMOS fabricated in an N-well. N-well means N-type diffuse tub or N-type diffuse region. Okay. So I have PMOS fabricated there, and the right hand side I have fabricated NMOS directly on the epi layer without any well. All right, and you just see that here actually by quick, while drawing it quickly, I don't have scope for wiping off. So what I have shown here, in fact, here you see that this N-well and the source are connected. There is a continuous metal. There is a hole here directly on the substrate which is N+. Please remember that. Please see that this region is N+, whereas from here to here it is P+. This is the P+ source of the PMOS, whereas this is the N+ source. This is the N+ source of the NMOS. Whereas this region again is heavily P doped, and this region is very heavily N doped. So please see the source and substrate shorted. Have you seen it properly? The source and substrate are shorted for the NMOS, and the source and N-well shorted for the PMOS. Please see it carefully. The source and substrate shorted for the NMOS, which is built on the P-type epi layer, whereas the source and N-well shorted for the PMOS. I have drawn it like this. Actually, it should have come. And the same kind of technology which I indicated in the last class, that we use polysilicon gate. These gate materials are all polysilicon. And self-aligned source drain formation, which I told you in the last class, that automatically by using an implantation, I can align the edge of the source drain with respect to the gate electrodes. The only additional thing which is very important here is that we have to adjust precisely the values of the threshold voltages of the two MOSFETs. This is PMOS, this is NMOS, and this is PMOS. We have to adjust the values of the threshold voltage normally for a 5 volt, if VDD is 5 volt, which is quite typical. In that case, VTN is around 1 volt, whereas VTP is around -1 volt. Typically, not exactly, but typically. So I have to adjust the values of the threshold voltage of the two MOSFETs precisely during fabrication. So you understand that technology is much more complicated than the normal NMOS technology, because we have both types of devices, both PMOS, and normally both are enhancement mode. That is the requirement. CMOS technology, please remember, both the load, and this is divert transistor and this is the load transistor. Both transistors are enhancement mode devices till today. They are very properly isolated by using oxide isolation. Then the question should come to me that why unnecessarily I use the P-type epi layer and this substrate, etc. P+ substrate and P-type epi layer. What is the need? That question should come to me. Any one of you? Any knowledge about it? Having any knowledge about it?
the question?
Louder.
What is the question?
Question is why I had to use in this technology a more complicated route where I have started with a P plus substrate. On this I have grown an P-type epi-layer. Instead of that, I could start with a P-type substrate and I could eliminate the epi-layer formation. That complicated epi-layer is a complicated process. Epitaxial growth, which I have indicated earlier in bipolar technology, in connection with bipolar technology, is a very complicated task. But here I have used it. And not only that, this is a very thin epitaxy. Again, very challenging. 1 micron to 3 micron reliable uniform epitaxy is not a simple task. People today are using still thinner epitaxy, less than 1. Why? Why I have complicated the technology like this? Yes, please. Have you heard of a phenomenon known as Latchup effect in CMOS? Any one of you? Latchup effect in CMOS? You have not heard of it. If you carefully examine this CMOS structure, you see that because of the presence of NOL, which is important, if I had not used the NOL, I could not have fabricated PMOS on the same substrate side by side. This has been possible simply because I have used this NOL. And in that process, you see one thing has happened. We have a device like this, PNPN. Just see, PNP and then PN. This is the ground side and this is the highest potential side. So I have got PNPN or PNPN. And what is this PNPN called? A thyristor, a switch. And you remember a PNPN layer. If you have a PNPN layer, let us discuss it. If you have a PNPN layer, say let me write VD. What is the characteristic of this PNPN layer? If you draw the ID, if I write it ID versus VD, this voltage I am calling VDD. So ID versus VDD. What will happen? Initially, because this is positive bias, this junction is forward biased, but this junction is reverse biased. Okay, and therefore, and what about this junction? Sorry, what I said, this junction is forward biased, this junction is forward biased, the middle junction is reverse biased. We have seen it. So initially, this will be like this. But ultimately, above a certain voltage called forward blocking voltage, you remember, suddenly there is a switchover of state from a high conducting state to a low conducting state. You remember that? This is a forward blocking voltage. So up to when the power supply voltage is from 0 to this voltage, this device will not draw much current. It will be just merely the leakage current. But due to any reason, if this VDD somehow shoots above that particular voltage, suddenly the device will turn on from a insulating, almost insulating, a non-conducting state to a very highly conducting state. And that is a major thing of a thyristor, you know, SCR. And by having a gate, I can influence this process. By having a gate voltage here, you remember that I can have characteristics like this. I can control the switching point. This is what is called latchup. Why it is called latchup? Because once it is turned on, it cannot be turned off until the voltage, the supply voltage is made 0 or reverse biased. If I do not make this VDD 0 or negative, this conducting state will continue. That is why it is called latchup. Nothing but a memory, a volatile memory. Same thing happens in the CMOS. Look for carefully. You see that we have an inbuilt PN structure in CMOS. And what happens, suppose the drain supply, while switching on, or any power supply source somewhere, if this voltage, we know that if you carefully look at the power supply voltage variations, you will find suddenly for some time the voltage may be very high, but maybe for a very short duration. That is, suppose the same power supply is running various installations. So various, say, power mode supplies here, switching the switch, what is called thyristor power modules or heavy motors, etc. As soon as you switch it on, you have got the reflection in your main power supply. That is why we use that regulated power supply. Then we also use that called isolation transformer, etc., which is so important today in a computer installation. We need a dedicated ground. We don't depend on a ground which is supplied along with the power lines. We need a dedicated ground, dedicated RF ground. We need a very good power supply, highly stabilized. We also normally want a good isolation transformer. These are all important to reduce the charge, the surge effect, the voltage surging effect. But anyway, for very short duration, the voltage may be as high as maybe, if it is meant for 5 volt, but actually for 5 microseconds or few microseconds, sometimes it may go as high as to 50 volts or even above that, which is normally not noticed. But CMOS will catch it up, unfortunately. CMOS will catch it up. And once this voltage rises above that so-called forward blocking voltage for this PNPN parasitic structure in the CMOS, then it will turn on. That is, between this point and this point, we have a short circuit, practically a short circuit. And the inverter will not work. Unless you switch it off and once switch it on, it will. So that is a very severe problem in CMOS circuits. CMOS technology came up and it developed gradually, but a very difficult thing with CMOS was to get rid of this highly undesired effect, which is called Latchup effect in CMOS. How to get rid of it? One simple technique to get rid of it is to use an epitaxial film, as indicated here. You have got a P plus substrate, then a P-type epi layer, so that this region is very thin. This is thin. So what will happen? Can you tell me? You see, there is effectively a vertical transistor here. One junction is forward biased. Then this is the middle junction. This is reverse biased. So there is practically a transistor. This is nothing but a lateral. You have seen that. That's how we describe a thyristor. We can divide a thyristor into 2 transistors, a PNP transistor and NPN transistor, where the base and collectors are merged. Okay? So same thing here. This is a vertical PNP transistor, and this one is a lateral NPN transistor. These are merged together to form the PNPN structure in CMOS. But in this case, I have put the P plus film here, very close. So what will happen? The injected holes, after passing through this layer, will be mostly, passed into the ground. Normally this is also kept ground. It will not go into this part. If it is not allowed to traverse this part, no question of latchup. Only with one transistor you can never get latchup. If there is a regeneration inside, the base of one collector of one transistor is automatically connected to the base of the other transistors. So there is a latchup circuit, regenerative latchup circuit. Then only we can have latchup. But that question does not arise if we put a P plus sink. This P plus is acting as a sink for holes, injected holes, which is kept very near the epitaxial, the N-well edge. And that's how this structure is practically free from latchup effect. You know that some other techniques are also used. Do you know any one of you? You have not heard of the latchup effect. Unfortunately, don't go through literature. At least you should have the habit of going through some journals, popular magazines, etc. Are you subscribing? Any one of you is also taking that member of IEEE? I think many of you are members of IEEE. If you are IEEE members, I think you get the journal called IEEE Spectrum. Are you getting? So IEEE Spectrum, if you go through, if you form the habit of, sometimes you'll find articles where CMOS technology, Latchup, etc., comes in. Similarly, many other popular, forget about the good journals, actual academic journals, there are many popular journals in the library, magazines they are called. You had these things are discussed. So that is, I expected that some of you at least know what is meant by Latchup. What is Latchup? You have not heard of, you said, Latchup in CMOS. This is unfortunate. Okay? So this Latchup is inhibited, almost eliminated to a great extent by using the epitaxial film. Alternatively, I think you have, that is why you do not know, people make trenches here. Between the NOL and the nMOS, a trench is formed in silicon by a suitable dry etching process. And the trench is filled up with oxide. So if you dig a trench here, and that trench means surrounding the NOL, if you dig a trench and fill it up with oxide, what will happen? You are inhibiting the lateral motion of holes. You are resisting the path, blocking the path. And this is what is called trench isolation. Initially, Texas Instruments was first using trench isolation technology for producing, but nowadays I don't think trench isolation is that popular. Most people are using isolation with very thin epitaxy. That's a very popular technology. Okay? So if you have understood the basic thing of this technology, I think it is not needed to discuss the details of the technological steps. It is much more complicated than the nMOS technology. It has all the features for the nMOS technology, but in addition to that, we have got the PMOS technology inbuilt. So if the nMOS technology requires 10 masks, this process will take more than 15, 16 masks in lithography. And then, many other things today, for example, you'll come to know about a technique called salicide. Have I mentioned that in the earlier class? Salicide, self-aligned silicidation, which is used also in nMOS. Similarly, the dual implants. People do channel implant for nMOS and PMOS, nMOS and PMOS separately. In certain technology, they try to manage that condition, achieve the condition VTN is equal to VTP, plus minus 1 volt, magnitude-wise, by using a single channel implant. In certain cases, people use dual channel implant, 2 independent channel implants, and it is a very complex technology. Unless you simulate the whole process properly and with very reliable technology bias backup, it is very difficult to fabricate a good quality CMOS. But fortunately today, almost all the industries are equipped with good CMOS technology. The famous vendors, their products today are all CMOS technology. Whatever new products you come to know about today, any new VLSI product, these are all CMOS technology based product. But with that, I have also already mentioned that bipolar and CMOS has now been combined, and people call the technology BiCMOS technology. And this is very effective for circuits where both analog and digital functions have to be integrated, known as mixed signal ICs. So today's trend is, technologically there are 2 technologies available. One is called CMOS technology for most applications. The other is BiCMOS technology for some specialized application. So this is the status today. Why people went for CMOS? Let us see that. I have discussed about the technology, let us discuss quickly the inverter circuit aspect. Okay, you see that this is the basic circuit of the CMOS inverter, single CMOS inverter. You know the advantage of CMOS, in the steady state, one of the transistors is always off. In the steady state, one of the transistors is on. When Vi is 0, this transistor is off and this transistor is on, and then output nodes charges to VDD, switches to VDD. And when Vi is high, VDD for example, this transistor is on and this transistor is off. So whatever charge which was accumulated here, that discharged, and so VO turns to almost 0. Discharge at the capacitor, the node here, it is connected to another such CMOS. The charge stored at the input gate of that inverter discharges through the driver transistor quickly. That's the feel. You know that in the steady state, power consumption in the CMOS is practically zero. Negligible. Whatever power consumption which we normally encounter in CMOS logic, and that is during the transition. When Vi changes from 0 state to 1 state, low to high, for a short time, both the transistors pass through the so-called, they remain on, active region. Both of them pass through active region. And as a result, what will happen? There will be power dissipation in both the transistors for a short while. And therefore, it is found that the power dissipation in a CMOS is proportional to the clock frequency. Higher is the clocking rate, more is the power dissipation in CMOS. Another important thing is the shape of the CMOS clock. If the CMOS clock is not properly shaped, that means if the transition region is not sharp enough, then we are forcing the transistor to remain in so-called active region for longer time. So it will draw more power. So be careful, not only the frequency, but the shape of the clock is equally important for optimizing the power dissipation in CMOS. We say that CMOS is practically zero power logic, but it depends on, higher is the frequency, there is some drawback for CMOS. Maybe nMOS will be superior at very high frequency. Okay? And we shall discuss, perhaps I'll try to find some time to discuss a very interesting bipolar logic which competes with CMOS, and that is what is called I2L, integrated injection logic, which does not have this problem. Integrated injection logic also consumes very little power, just it is comparable to CMOS. But here, in that case, it is not dependent on the frequency of the clock. So CMOS is good, but then this is the main drawback of CMOS, that if you go to very high speed clock, then there is little problem, because after all, it has to pass through the linear regions, it's the active regions. Now, what about the packing density, etc.? If you now compare the CMOS inverter with the other inverters so far discussed, what is your comment? Do you have to satisfy the condition that the beta ratio should be very large? We shall discuss this point afterward, but it can be shown that that condition is not important. Only thing is, usually beta R is roughly equal to 1, but not exactly. Beta R is actually equal to mu p by mu n. Little bit less than 1, very little bit less than 1. Mu p means hole mobility, and mu n is the electron mobility. It can be shown that the driver transistor, for optimal operation, the driver transistor should have a W by L ratio which is in fact slightly less than that of the load transistor, which is just the opposite for the other cases. You have seen in all other cases, the diverse transistor should have a much higher W/L ratio compared to the load transistor. Then this VOH is again equal to VDD. It's a very good, it's a positive feature. So if you compare now the features of CMOS, you can write one down thing is, you know, VOH is equal to VDD, positive feature. Logic swing, VOL can be very low. VOL can be very low. That means this type transistor can be properly designed so that the entire charge gets discharged. So the voltage falls down to almost 0 volt, because this becomes off, isn't it? When this is on, this is off. Whatever charge will be there stored in the capacitance at this particular node, it will fully discharge. So it is expected the VOL will be very low, almost 0. The logic swing is very high. And this beta R is very less, means high packing density. And very, very low power domain. And that is, of course, the most important thing. These are, I think, some of the positive features of CMOS. But can you mention some negative aspects? What about speed? Suppose if you compare 1 micron nMOS with 1 micron CMOS, please remember the minimum size should be kept the same for comparison sake. That is very important. 1 micron nMOS, by 1 micron I mean the minimum feature size. In this case, what is the minimum feature size? Channel length. Whenever we speak of MOS technology, minimum feature size is a channel length. Okay? So 1 micron nMOS and 1 micron CMOS, if you compare, which one is better from power dissipation point of view? CMOS. But speed or propagation delay point of view? CMOS, nMOS, definitely. Because now there is an additional well. And this N well, there is a charge, you know, there is a parasitic transistor here. And there will be charge storage, and ultimately which gives rise to more delay. This is an additional problem. More capacitances involved. More parasitic capacitances. So many junctions are there. And naturally, it adds to the delay. It increases the delay. But then people are saying that CMOS with 100 picosecond, 50 picosecond. Then what is that people have done? Simply by miniaturization. CMOS has gone to that extent of tens of picosecond, almost tens of picosecond have been, hundreds of picosecond already there. But tens of picosecond in the intrinsic delay has been achieved in CMOS technology simply by sub-miniaturization. People have made all these things extremely small in size. You know that today's technology, people are speaking of 0.1 micron CMOS. Minimum feature size 0.1 micron. Scale down from LSI era of 5 micron to 0.1 micron today. Of course, the products which are available today in the market, they are usually 0.7 micron products. The technology is 0.7, 1 micron to 0.7 micron. That is the today's product range, whatever available in the market. But futuristic products, which will come within a few years, will have 0.1 micron channel length. So naturally, because of the tremendous advantage which is gained by miniaturization, CMOS, in spite of the fact, comparably, if you compare nMOS and CMOS, nMOS definitely will have this shorter delay for the same minimum feature size. But added with the fact that CMOS consumes very little power, very, very little power compared to nMOS, the sub-micron CMOS with its 100 picosecond kind of delay is a highly attractive thing, very attractive product. And that's why nMOS has been totally substituted. No, nMOS exists only for certain applications like RAM memory circuits kind of thing. But so far as logics are concerned, it is totally invaded by CMOS. Now, I told you that the two FT, two betas, this is called beta of, sorry, two threshold voltage, beta, VT of PMOS and VT of nMOS. I said that this should be the same in magnitude. One is usually for 5 volt, typically I told you VTN is around 1 volt and VTP is around minus 1 volt. Why this need? Any one of you from common sense? Why this need? Was it possible, suppose VTI make 1 volt, but VTP minus 3 volt? Do you recommend it? If you compare, if you just try to understand, you already, I think you studied the CMOS basic thing, the digital electronics course. You know that this, when Vi is 5 volt, this is, and suppose this is 1 volt, the threshold voltage is 1 volt. When Vi is 5 volt means 5 volt is 5 times more than the threshold voltage, very heavily on. A very strong inversion layer will be formed here. When I make Vi is equal to 0 volt, and this is 5 volt, so effectively VGS of this device is minus 5 volt. And if the threshold voltage of this transistor is minus 1 volt, so you just see that in this case you are applying a gate voltage of minus 5 volt to a device which has got a threshold voltage of minus 1 volt. So what are you doing? You are doing the same thing. You are expected to achieve a saturation inversion layer of the same strength as in the earlier case. Then only we will get symmetry in the characteristic. Otherwise the whole characteristic will shift. We need exact anti-symmetry of these characteristics around a point which is roughly VIH by 2, this divided by 2. Then only we can achieve the highest noise margin. If the characteristics were like this, is it preferable? Or it is like this, is it preferable? Which one is most preferred? The central one. This is possible only if we satisfy the condition that VTN is equal to magnitude of this is equal to magnitude of this, both enhancement mode. And you know that you can tell me, sir, why it is we don't make it exactly. Suppose it is 5 volt. Why don't you design with 2.5 volt, 2.5 volt both? Then you are expected to get a characteristic almost a vertical one like this. Am I correct? If I, or not? Anyway, we shall discuss this point afterward. But please note that we always need, for the proper placement of this characteristic, that to achieve the same order of noise margin for both high and low states and high noise margin, we have to make both the transistors very similar in nature so far as their DC characteristics are concerned. That means we should try to maintain VTP equal to VTN magnitude wise. But their sign, their polarity should be opposite, because it is PMOS enhancement mode means the gate voltage should be negative. nMOS enhancement mode means gate voltage should be positive. So these things should be kept in mind. Okay? Thank you.